So mathematically, what is a singular value decomposition? Well, by definition, a singular value decomposition is a matrix factorization that looks like this. A equals U times sigma times V conjugate transpose. In this factorization, A can be any m by n matrix with rank equal to little r. So what are we doing? We're taking our matrix A and we're expressing it as U times sigma times V conjugate transpose. U here is an m by r matrix with orthonormal columns, meaning that U star times U equals the identity matrix. Sigma in this factorization is a diagonal matrix whose diagonal entries are noted by little sigma 1 down to little sigma r. And finally, V here in a singular value decomposition is an n by r matrix whose Gramian is the identity, which again means that the columns of V are orthonormal. So this is a singular value decomposition. One thing to note here is that there's no stipulation on what type of matrix A can be. If you give me any m by n matrix, what we'll find is that it's guaranteed to have a singular value decomposition like this. Now, there's some terminology attached to, that we introduce here. Typically, when we're working with a singular value decomposition, we rank the entries on the diagonal of sigma, and these are all numbers that are positive. So sigma 1 is greater than or equal to sigma 2 all the way down to sigma r, and these are all positive numbers called the singular values of A. Furthermore, we can use all of the data in a singular value decomposition to construct what's called the rank K approximation of our matrix. This is given by A is approximately equal to the first singular value multiplied by the first column of U multiplied by the first row of V conjugate transpose plus the second singular value multiplied by the second column of U multiplied by the second row of V conjugate transpose. And then we keep going until we get to the kth singular value, so this little r should be little k, multiplied by the kth column of U multiplied by the kth row of V conjugate transpose. So let's see an example. So here's our first example of a singular value decomposition. So here we have some matrix A, and this is expressed as a matrix U times sigma times V conjugate transpose. Here, U and V have orthonormal columns. So what is our compressed sum in this situation? Our compressed sum takes our matrix A and then expresses it as a sum, a weighted sum of columns of U multiplied by rows of V conjugate transpose. We start with our first singular value, which is equal to 5 here. That gets multiplied by the first column of U times the first row of V conjugate transpose. Then we move to our second singular value, that's equal to 3 here, multiplied by the second column of U, multiplied by the second row of V conjugate transpose. So this is an E-quality. This is simply another way, a messier way to write the singular value decomposition. Now, the rank of this matrix has to be 2 here because this matrix has 2 singular values. What about the rank 1 approximation? Well, for the rank 1 approximation, we look at our compressed sum and then we drop all but the first term. So the rank 1 approximation here tells us that A is approximately equal to the first singular value 5 multiplied by the first column of U multiplied by the first row of V conjugate transpose. So that's the rank 1 approximation. We can calculate this rank 1 approximation because we have our singular value decomposition. And if we do the arithmetic here, this ends up equaling a matrix with whose rows are both the same, 5 halves, 0. So this is not equal to A, but it's considered the best rank 1 approximation of A, which has rank 2.